Welcome back to our course series on advanced hydraulics. We are in the first module. The module name is open channel flows, and we are into the 9th lecture of this module. In the last class, we had gone through the following topics: critical flow, critical slope, section factor, hydraulic exponent for critical flow, non-dimensional graph, how to develop the non-dimensional graph of the section factor versus the depth of flow. If you recall them, we had developed them, those graphs and all. We had even solved one problem for a rectangular channel. We had solved the problem using trial and error method. We asked you to do them as a homework and see what is the value you are going to get and all. Maybe most of you might have got the critical flow approximately around 0.756 meter and all. The same problem you can again solve using the design curves or design tables you had developed. We had developed the non-dimensional graph of section factor versus depth of flow. Similar, using that for the rectangular channel, you can again solve the above problem. Let us see how you can do with the following situation. First, you need to compute for the given data, compute Z, that is the section factor Z. You know Z is equal to Q by root G. For the given problem, Q was found to be 6 meter cube per second, and you know what is the value of G. So, then your section factor is identified as 1.916. What is the non-dimensional form of this Z? So, you just evaluate Z by b to the power of 5 by 2. You know what the given value of b is 2.5 meter. Therefore, Z by b to the power of 5 by 2 is, I will just rub this portion, you will get this quantity as around 0.194. So, you use the same graph of rectangular section factor versus depth of flow. The same graph, if you recall them, see from this graph, for the rectangular, any rectangular cross section, you just check what is the Z by b to the power of 5 by 2. It was given as 0.194. You just check it where the depth is coming. This is coming roughly 0.194 is coming roughly around somewhere here. You will get the corresponding y by b ratio. Say somewhere here, you will get some roughly around that value. You can take that y by b value and try to evaluate what is the depth of critical flow. You can use the same tabular form which we had developed. So, this is the tabular form y by b for the rectangular channel, and you can see that from that the 0.194 value, this 0.194 value lies somewhere in between 0.3 and 0.4, right. Use that value now. So, let me suggest that it is around 0.3 0.31 or 0.32, something like that. So, from the z by b to the power of by 2 versus y by b graph, you got y by b approximately around 0.305 or something, b is equal to 2.5 meter. Therefore, your critical depth of flow is around 0.755 meters, something like this. Fine. Like this also you can determine the depth of flow in a rectangular channel. For the next portion which we want to discuss with you is that your critical flow concepts. The concept of critical flow they are also used in channel transitions. So, what is meant by channel transitions? Say a channel, if you take the longitudinal view of a particular channel, say if this is the depth of flow is in this direction, this is the vertical depth. If in the channel bed, if any hump is being constructed or hump arises, what happened to the flow? This is one type of channel transition. Or if you take the horizontal view, this is the width of the river or channel. If all of a sudden it gets constricted or enlarged, vice versa, what happens to your flow? So, these are some of the channel transitions that one can study. So, if there arises hump in the flow, or if the width of the channel changes. So, let us see for these two situations how the flow changes or how you can compute the flow parameters. So, first, if there arises a pump, if there arises a hump, what happens? For our demonstrative purpose, let us take only a rectangular channel. We are only considering a rectangular channel. Its width is b. So, if you take the longitudinal profile, say at a particular cross section, this is the depth of flow, y 1 is the depth of flow in that rectangular channel. A hump is situated somewhere here downstream and not that far, and let us consider a cross section at this location. What happens to your flow? This was the depth of flow. Now, you may see that there will be some change in the flow pattern. Initially, let us consider subcritical flow at section 1,1. So, if the flow is subcritical, again I will just draw for your purpose. There is a hump, smooth hump. So, we are just taking the section 2,2. So, the subcritical flow depth y 1, for this you have seen how the specific energy versus depth of flow curve is there. So, for this depth, this is the corresponding energy E1, right. Then you can use the same concepts whatever you have studied. Just go back now, you will see that as the stretch is not too long, that is the distance between section 1 and section 2, it is not too long. We assume no energy loss, that is the total energy between these two sections are not going to change. This is an assumption we are going to incorporate. If this assumption is there, what will happen then? You will see that at any section total energy is total energy you have means datum energy plus your specific energy. This will give you the total energy at any cross section. So, based on this datum energy means nothing but the potential energy. If you see the same relationship now at section 1, your specific energy is E1 at section 2, the total energy is same. However, due to the hump here, there is change in specific energy at section 2. So, we will see what is the change. Again go back to your E versus Y curve. So, this was your depth of flow at Y1 at section 1, and the corresponding energy at E1. The total energy being constant, you have to see that there is a raise of elevation. If you see the previous section, there is a raise of elevation at this location by a magnitude say del y. Let me give this as a del y. Then that amount, the bed is raised by an elevation of del y, you will see that the energy, specific energy at section 2, it is nothing but E1 minus del y. Keeping this in mind, from this graph, you just deduct the amount del y. Say if it is something around here, then this is your E2, specific energy E2, extend it into the graph and you will get your corresponding depth of flow Y2. So, if for a subcritical flow, you will see that due to the change in elevation, due to a hump coming into the picture or hump arising in a flow, this will cause the depth of flow at section 2 to depth of flow to reduce. So, that the specific energy, whichever specific energy as it is getting reduced due to the hump elevation, the height of the water is also reduced subsequently. That can be seen from this particular graph. Therefore, elevation at section 2 will, or the level of elevation of water surface, or the water surface, it will reduce at section 2. We can see the same portion. Similarly, what happens if in this particular situation, if your depth of the, if your height of the hump or the hump height, if it increases further? From this graph, it is quite obvious, it can increase up to this particular portion. So, this will be the minimum specific energy possible at that particular cross section. At section 2, this is the minimum specific energy. So, E c, you cannot reduce the specific energy below E c. So, you can see that at what location E1, E2 is becomes the critical energy. Let me give this as del y m. So, beyond this, what happens then, or at this height what happens? Your flow becomes critical. If E2 is equal to E1 minus del y m, then E2 is critical condition, y2 is equal to critical flow depth, and the flow in section 2 will be critical. If the hump height, if your hump height is greater than the height that is required for critical flow at section 2, what happens? Now, you have to think on your own self. Again, go back to the curve. Here, if from E1 minus del y m will give you the critical energy at section 2 E c, and if if your hump height is greater than del y m, your critical energy cannot, means your energy at section 2 cannot go beyond E c. That is not theoretically possible at all. So, what happens? So, your energy at section 2 will remain at critical condition, that is whatever is the critical depth and critical flow. From there, you need to add del y m. So, E c plus del y m. Okay, I will just give it in the next slide. E c plus the del y, that will give you a new specific energy at section 1. So, you need to incorporate this thing, that is in the graph this will go from here. If del y is greater than this, like this, then this portion E 1 dash will come into picture here. You just elaborate that, see from the graph, and you will see a new depth of flow at section 1. So, such situation arises. Now, you can see how the critical flow is being applied here. If the flow, a subcritical flow in a channel section, if there arises a hump, you will see that the minimum possible is that flow will become critical at section 2, and If the hump height is still much higher, then the flow at section 1 it changes its specific energy and it raises its elevation. So, at section 1 the depth of flow increases. So, this is an increased depth at section 1. So, in the presence of hump in the rectangular channel, first you need to evaluate specific energy at downstream, pardon me, I beg pardon, at upstream section. E1. So, E1 you know for the rectangular section it is nothing but y1 plus q squared by 2g b squared into y1 square. Now, calculate E2, that is the specific energy at the downstream section. E2 is equal to E1 minus del y. Once you compute this, you have to check whether E2 with respect to the critical energy at section 2. For critical energy at section 2, you know this is for a rectangular channel, this is nothing but 3 by 2 into phi c. This you have already derived that in previous classes. So, if your computed E2 comes less than E c, you have to take E2 is equal to same as the critical energy flow or the energy at the specific energy at the critical flow, then compute specific energy at upstream. This is the modified specific energy at upstream section E1 dash. This is nothing but E c plus del y. Del y is the height of hump. So, once you compute E1 dash from E versus y graph, find modified depth y1 dash at section 1. You can easily see that if I plot depth of flow versus hump height, as we had assumed that initially at the upstream section the flow is subcritical. So, you can just see for the various values of the hump height del y what will happen. The depth of flow initially it is subcritical and it will remain at section 1 it will remain at same elevation for a considerable time. Once it reaches the critical del y m value, then you will see that on further increase of the hump, your depth of flow will gradually increase at section 1 1. Similarly, at section y 2, you can plot the following situations. You will see, say it is starts at y 2, then it goes on decreasing as the height of the hump increases. It will reach at a particular level. Here, this is your critical depth, and from here the section 2 will maintain the critical flow condition itself, whereas at section 1 the elevation of water will increase. This is how you can interpret the following graph, or you can easily draw them. I would like you to do it as an assignment. What happens, say if at upstream section the flow is supercritical initially. What happens if there arises a hump at section 2 or at downstream section? If there arises a hump, what will happen to your flow, or what will happen to the depth of flow? This you can do as an assignment. It will be better if you can work it out at home and see. Now, the next channel transition we mentioned was change in width. Again, we are mentioning that for the demonstration purpose, we are using only the rectangular channel. You can use the same concepts for other cross sectional channels also. So, let us consider a channel stretch this is your section 1 1. This is the top view or the horizontal view of your channel. Here the width of the channel is B 1 and it gets reduced at downstream. To B 2. In fact, you can even draw the elevation of water based on this top view, how the elevation of water looks also. Like that also you can interpret them. So, for such type of channel transition, how will you infer the depth of flow and all? You use the same concept. Again, we are assuming that this is frictionless flow or total energy is constant, or the energy in the flow, energy for the flow, this is constant, there is no energy loss due to friction and all, we are assuming like that. At section 1 1, you have your specific energy E 1. E 1 is equal to y 1 plus V 1 squared by 2 g according to our formulations. This is nothing but y 1 plus q squared by 2 g v 1 squared y 1 squared. Similarly, you have specific energy at section 2, this is E 2, this is y 2 plus v 2 squared by 2 g, E 2 is equal to y 2 plus q squared by 2 g b 2 squared into y 2 squared. So, from these two relationships, you can easily see that your specific energy is nothing but the depth of flow plus q by b whole square by 2 g y square. You can even try to analyze the quantities in this way, in this particular form. If width of the channel decreases, then you will see that q by b 1 is less than q by b 2, because b 2 is less than b 1 and you have the same discharge. There is no energy loss between the two sections 1 1 and section 2 2. As it is a frictionless channel, you can see that E 1 is equal to E 2 in this case, because there is no change in bed elevations, right. There is no change in bed elevations. Therefore, E 1 is equal to E 2. From the following equation, one can see that E versus y curve for different q by b values, one can interpret them. How will you do that? If I try to interpret, say, for different q by b, for different depth of flow and E, if I try to compute it in a table, say you can start with q by b is equal to 10, 20, 30, then for different depths the E, like this. If you try to compute them, you will see that you are going to get the following type of curve. You will get a following type of E versus y curve for different values of q by b. This is for q by b, q by b 1, q by b 2, q by b 3, q by b 4, like that you can just draw it. So, different values of q by, for different values of q by b, you will get different specific energy curves of the following form. In the rectangular cross section, as q by b 1 is less than q by b 2, what happens to your curve? In the above graph, you have seen that, say, for lower values of q by b, these are the curves. For higher values of q by b, these are the curves. You interpret them again in the same form. At the upstream section, q by b 1 is a lower value, and this is a higher value, right. in this particular channel section, compute Q by B1 and Q by B2 first, then go back to the curve. You have to interpret, say, what is from this curve. Say for Q by B1, this was the initial depth of flow available. This is the depth of flow at the cross section 1 1, fine. Then on channel restriction or the width getting restricted, it will go into the next curve Q by B2 or whichever is appropriate, and you will see, let us assume that Q by B2 is the respective curve. So, here at section 2 2, the depth of flow will get reduced to y 2 as per the following graph. That is, this is the channel bed, here is your y 1, then as the channel width decreases, the depth of flow at section 2 2, it reduces to y 2. Similarly, in the case of hump, you have seen that y 1, then due to the hump here, the flow reduces to y 2. So, the same theory, we are using the same principles everywhere, critical flow computations. So, in this case, what happens? Suppose your Q by B2 or Q by Bi, your Q by Bi or Q by B2 at the Q by B at the downstream section, Q by B at downstream section, whichever curve is coming, if this was the curve, what happens then? Now, here you will see that the energy curve which has been computed at section 1 1, that curve is not intersecting this curve at any location. So, therefore, the depth of flow or the energy, the same specific energy is not available at section 2 2, that is what it can be inferred. In such case, what happens to the flow is that for the given cross section Q by B, whichever is the critical energy for the same curve, that will be taken as the specific energy at section 2 2 from, if Q by B curve is higher, if Q by B value is higher and the specific energy is not found for the upstream situation, then you have to see that from the same curve you have to take the situation where, say, if this was the curve, you have to take your minimum energy, if this was the original energy at section 1 1 y 1 and this is E 1, then you take at section 2 2 the minimum energy section 2 the minimum energy possible is then E c, because this is the curve for that particular cross section q by b. This is the available curve. So, the minimum energy in that available curve is at this location. So, you have to take that as the minimum specific energy at section 2, you extend it and you see at which location this portion comes. So, you have to see a new modified specific energy at 1 arises. This is called E 1 dash. This is called E 1 dash, and you can see that this is same as the critical energy at section 2. So, what is the corresponding depth of flow y 1 dash? Y 1 dash is the new depth at section 1 in such situations. So, you have now seen two channel transitions now. For the second case also you can do as an assignment, if supercritical flow at 1 is present initially, then what happens? You can do this as an assignment. Let us do a numerical problem based on these two cases. A rectangular channel upstream width is 3.5 meter. It is reducing, the width of the channel is reducing to 2.2 meter. The flow is 2.8 meter cube per second. Bed level at section 2, that is at downstream, raised by 0.12 meter. We are neglecting energy loss. Now, find the depth of water at the downstream location. Can you do this problem? Let us see how this example is working out. As you know, the channel bed is of this type. At the upstream section, the depth of flow is y 1 equal to 1.1 meter. Downstream, a smooth hump is placed, and as we have seen according to our theory, the flow may be something of this type, and we need to evaluate the depth of flow y 2. For that, first you need to evaluate the specific energy at section 1, that is at the upstream. E 1 is equal to y 1 plus q by b 1 whole squared by 2 g y 1 square. This comes out to be 1.1 plus 2.8, or you see I can just rub it out, make it a single notation. This is coming out to be 2.8 by 3.5 whole square by 2 into 9.81 into y1 squared is 1. So, this comes out as 1.127. You have to also check whether flow at upstream section is subcritical or supercritical or critical, right. For that you have to evaluate the fluid number, we had studied that, the average velocity at the cross section divided by root of g y 1. V 1, what is V 1? V 1 is equal to q by V 1 into y 1. This is coming out to be 2.8. .7272 meter per second. So, your fluid number using these data, it was coming to be around 0.22, which is less than the required criteria. So, fluid number less than 1 means the flow is subcritical. Similarly, evaluate q by B 1 and q by B 2. You know q by B 1 is equal to 2.8 by 1.1, q by B 2 may I beg pardon, q by B 1 is 2.8 by 3.5, and here this is 2.8 by 2.2. So, you have the respective curves of q by B, means you have the respective curves of E versus Y for different q by B's. You obtain those things. Q by B 2 is found to be, it has been found to be 1.2727. What is the critical flow? What is the critical flow at section 2.2 or the downstream? Critical flow is the flow, means it is the only one type of flow, critical flow at section 2.2 for the given channel cross section, that is your width is 2.2 meter channel cross section. Your critical depth, it is coming out to be q squared by V 2 squared g this is nothing but your 1.2727 whole square by 9.81 whole to the power of 1 by 3 0.5486 meter. Therefore, the critical flow possible at section 2 is 3 by 2 y C 2 is equal to 0.823 meter. So, you know at section 2 the critical energy possible is 0.823 meter. Also, a hump is placed at downstream, that is section 2. The elevation of hump as per the data is equal to 0.12 meter. Therefore, the specific energy at section 2 is at the downstream is nothing but the specific energy at section 1 minus del y. This is coming out to be 1.127 minus 0.12 meter is equal to 1.007. This value is found to be greater than the minimum possible energy at section 2, and therefore, there will not be any change in elevation at upstream section 1. So, let us conclude this module with this problem. We are even concluding this module. In the next lecture, next day's lecture onwards, we will be going into the second module on the uniform flows in open channels. So, I request you to go through the books and have some idea before coming to the class what is meant by uniform flow and all. Thank you.